of the number 24. And then the fancy name for these numbers from chapter 3 is divisors. So these are also called the divisors. I forgot the S. So all the numbers, all the positive numbers that divide into 24 evenly. So what's in the set A? I'll quickly jump on the easy one. One goes in evenly. 2.
4.
3.
4.
4. This is one of my favorite
6.
numbers because it's so rich. It has so many divisors.
No, you're
6.
factoring, yeah. 8.
12.
24.
It's possible on the practice test I posted on Canvas, that might be their test question might be about that set. Okay, so there's a bunch of numbers and they can be related to each other in various ways. Let me try first, I'm going to number these two relations. So R1, and I'll make this one be a mod relation. So I'm going to say A is related to B if and only if A mod, it doesn't matter, 5 is the same as B mod 5. Why did I pick 5? I have no idea. Usually we pick a prime number when we do this, meaning the 5, the thing we're modding by. Now we can take, we're going to try to analyze this relation and check it for all the different properties. And you can take the high road, you can take the more pedestrian road. We could do what we did on Thursday, which is start constructing the directed graph, which is I think what we did on Thursday. And then slowly as I was putting the arrows, I started saying things like, wait, everybody's going to be related to themselves. And I started going really quickly. So we could make the digraph, or we could try to be more sophisticated and see if we can practice using the definitions. I knew you were going to say that. Okay, let's be sophisticated.
Where are my glasses?
Everyone should wear a tuxedo to the final. All right. So let's check for reflexivity. So in the context of this question, what I wrote over there is very generically what reflexive means. Is every element in the set related to itself?
Yes.
So in our context, I want to convert that to what the relation is. So here we're asking for all numbers in our set A, and then I'm just going to write this down, but when we're checking for reflexive, those are both the same number. So for every A and A, does A mod 5 equal what if we're checking for reflexivity?
A mod 5.
A mod 5. Does A mod 5 always equal A mod 5?
Yes. Sure does.
Yeah, identically so, yes. So rather than have to do any number crunching with individual numbers, we're trying to be a little more sophisticated. Yes, every number has the same remainder when we divide by 5 as its own. So if I were to make the directed graph, every one of those numbers in the graph would have a loop in it saying, yes, I'm related to myself. Okay? How about symmetricity? Symmetricality? Yes. Yes.
Symmetried.
For all A and B in the set A, if A mod 5 is equal to B mod 5, then what should happen if the answer for symmetry is going to be yes?
B mod
B
5
mod
equals
5
mod five.
equals A mod 5.
Excellent. Becoming algebraists.
That was the other question.
No, I'm not. Does B mod 5 have to equal A mod 5? Yes. And really, the reason the answer to that one is yes, and the reason to that one is yes, the equals relation actually is reflexive, symmetric, and transitive. So we're kind of using that because this relation is described that way. Yes. So bam, we have reflexive and now symmetric. So that was yes, yes. And then what about, how would transitive look? I'll leave that part off because I don't have a lot of space here. If A mod 5 equals B mod 5, and B mod
Mod
5
Equals C mod 5.
excellent equals C mod 5. So this is, in this context, this is the way to describe a two-step path from A to C.
And then A mod 5 is equal to
And
C
then we're
mod
gonna be asking the question, must
5. A mod
mod
5
A mod
equal
5
equal
equal C
C mod
mod 5?
5.
Yes, because that's how equals works. Yes, so does A mod 5 equal C mod 5? Yes. What if one of them was mod 5 and the other one was mod 7?
No.
I would too. It never is though, it's always the same number. Alright, so why I did this first was just to bring down the enthusiasm level. I was trying to overdamp you. Mission accomplished. And so I'm not gonna start out the way I did on Thursday by making, like randomly putting dots for these points and putting the arrows every which way and then finally realizing that things could come together. Oh, I'm sorry, so I stopped here, we can check for it. I checked for these three, did I not mention why those,
You said it was a combination.
oops. Yeah, sorry, so this this combination is a certain type, yeah, so let me actually, I'll write a couple things, but we should check for anti-symmetry while we're here.
Is it okay?
Let's check for anti-symmetry. And this particular type of relation, a mod relation, in general, it is not anti-symmetric, but it depends on what the underlying set is. So, anti-sim. Anti-sim. So this is asking a question. If A mod 5 equals B mod 5, and what?
B mod
B
5
mod
doesn't equal.
5
Doesn't
equals A mod 5
It can only have two.
must, does it have to be the case that
A equals A.
A equals B?
no.
No, what are we doing, mod
Mod 5.
5? No. And since since all of these properties really are saying for all A and B in the set, whatever, we can come up with a counterexample. We can come up with one scenario where that doesn't happen. What's 1 mod 5? 1?
1.
What's 6 mod 5?
1.
1. So 1 is related to 6, and 6 is related to 1. Does 6 equal 1?
No.
No, not anti-symmetric. it doesn't satisfy that. So the answer, often, not always, but often if you're gonna try to demonstrate that a relation doesn't have a particular one of these properties, we give a counter example.
Sorry, I think that's what you just said. So just to prove that it's not, you just give one
Yes.
example for these because.
Yes, so to prove that it
Oh, because it's for
is,
all.
you gotta actually prove it, cause it's
By
for all.
exhaustion.
And if you wanna prove that it doesn't satisfy the for all, the easiest way is to come up with one specific concrete value and explain why. But sometimes the proof is, well, if this relation did have that property, we give kind of a proof by contradiction. We say, well, if the relation did have this property, then gravity would push things up, or something, you know, like we try to reason our way towards a conclusion that we know is false. But usually, for our purposes in this class, counterexample. All right. You ran out of enthusiasm like 15 minutes ago, but I'm just pretending I don't notice, and we're just plowing forward. But as far as we're gonna get, I just wanna make the, because we did do this last Thursday, but we were a little rushed. So typically, we check these, and then I say, I am gonna draw the directed graph for this relation, but I know all the elements are gonna have loops on them, and I know that all the streets are gonna be two-way streets, and the transitivity is the one that clumps the elements up in little subgroups that stay separate from each other. So when we draw this, we can draw this if we want. But I'll try to give us two ways to describe this. So for that relation, the mod 5 relation, we could either make the digraph this way, so we make it after the fact, and I'm gonna put everybody next to their partners in the graph rather than just put a bunch of random dots. So who's related to 1?
6.
6, anybody else? Anybody else have a remainder of 1? Mod 5? Okay, how about 2? 12? 2 is gonna go with 12. 3? 8. So they both have a remainder of 3. Oh, this is kind of boring.
4 and 24.
4 and 12. 4 and 24. Yeah, this is very boring. Okay, 4 and 24. So there's 2 ways to go here. If I still somehow wanted to think I'm making the directed graph, I would have all these little clusters of completely filled in arrows. So these are each forming like their own little secret club. So 4 relates only and in all possible ways with 24 in itself, and they don't communicate with anyone else. 3 and 8, same. They stick together and they stay away from everyone else. So these are referred to, the whole thing here is a directed graph, but these individual little subgraphs, so do you get what I mean? Like there's not some point where the 3 says, I'm sick of 8, I'm gonna go visit 4 for a while. No, they stay in their own cluster. And those little clusters are called equivalence classes. So for the purposes of doing mod 5, 1 and 6 are completely interchangeable with each other. And they're totally different from everybody else in the other groupings. So these are called equivalence classes. And in our textbook, they're not even going to put the arrows. They're going to say, if you're even reading the words equivalence class, you better know that I'm not drawing the arrows, and it's just written this way. We say 1 and 6 go together, that's an equivalence class. I'll actually write them this way. 2 and 12 go together. And the implication of this notation is that, within these individual subsets, all possible relation arrows are showing. And I think what your book is also gonna do is, this is kind of silly notation, but we often pick one member of each of these equivalence classes to represent the class. Just like the class president or whatever. So the 1 and 6 say, okay, I want to represent all the numbers whose remainder is 1 when we divide by 5. The representative could be 6, it could be 1, it doesn't matter. Our book is always going to pick 1, and your book is going to write this way. That was a lot of talking for an hour and a half to be able to put that line over the top of the 1. What does that mean?
That was not, right?
It used to mean not, doesn't anymore. In logic, it means not. So that means for the equivalence relation mod 5, that 1 with the bar over the top represents 1 and all the other numbers whose remainder is 1 when we divide by 5. So the 1 is representing a whole bunch of other numbers. 11 would be in there if 11 were in our set A. 101 would be in there. 926 would be in there. Like, all these different numbers are in the background saying, hey, that 1 represents me. Because it has the same remainder when divided by 5 as I did. Okay, I'm sorry. I'm getting panicky here at the end of the semester. So please look at what's on Canvas, the practice test in the files area, and see if you can see something like this on there, just to